لو اقول لك اني بحبك الحب شوية عليك انا ببعد عنك برجع مشتاق لعينيك ضمني خليك
Good morning, students. I see that the attendance is very, very poor. It's 55. It's too little to conduct, I think, a class. So, you see, generally, all colleagues, what they are doing, they are conducting the class online if it is cancelled or adjourned due to bad weather conditions, right? So, I sent an email in the morning, and I told you to check your email several times a day, right? I said that because otherwise you won't receive the communique. Now, those who are around, right, please do me a favor, contact your friends, the friends that sit with you in the class, or those who know who are not around, and tell them to join. Right? And please, class reps and vice class rep, I hope you did your job. If you have any private channels, right, send them, let them join. We'll wait a bit. Normally, around 94 students attend, not everybody. Last time when there was oh, you already informed them. Thank you, Mohammed, Tariq. No, thank you very much. Now, if they don't join, then this is their problem, right? Just like lectures face to face, if they don't attend, I can't do much about it. So let's wait a bit more and see. So do you have a group for each batch? You need to have one, I think. The other batches that I service, they have a group. But anyway, it's a small group. Oh, you have a group for everyone. That's very good. That's very good. Other batches also, I think, they have a group, and if they want to circulate a message, they just send it to the group. Right? And now it's up to members of the group to check. You see the correspondences or communicates from time to time. Now, okay. So I think let's wait a bit more. All right, let's also join. So those who can't find their friend here, that is the one who sits next to you, can you just send them a message? Tell them that to join the class. If you have some 94, normally 94 is okay. I saw 94 was present last time, 1994, then we can start. So I said 60, it has grown up to 60. You see, I don't know whether this Friday we will get a room. This room is not for our faculty, right? They were kind enough to allocate this lecture room to us, right, our BLT. But I don't think this week we will get it, so it's best to conduct the lecture online. Okay, now we have 61. I think it will grow from time to time. Let me see what we will do. Because we are moderately late with the syllabus, with the lectures. And I'm having a problem with this computer. So many things are not working here. So, lecture materials, lectures. Now, listen first. You would recall that I did connection-oriented and connectionless, right? So I told you that these are two main protocols that are used, right? There are two main protocols. One is used for connection-oriented. This is TCP, right? And the other one, UDP, is used for connectionless, right? Now, so connection-oriented, it's TCP. It's when we have to send a piece of data or whatever you want. Right? It's broken down into packets, right? So packets have maximum size of around 65 kilobytes or 65,525 bytes. Right? It's roughly 65. So then, based on the size of the data, it is broken down in packets and sent. Now, if you use TCP, right, all the packets has a sequence number, right? They're acknowledged when they reach the other side, right? And also, lack of acknowledgement means that the packet have not reached, right? So it needs to be retransmitted, right? And also it enforces something known as flow control, whereby if there is a very fast sender and which is overwhelming or overburdening a small receiver with more packets that they can receive, they can handle, then the fast sender should slow down. That is, look, you're sending too much, you should send less, right? So this technique is known as flow control, right? Now, I will polish it further as we proceed with the lectures, right? So this is barely roughly, in fact, it works with something known as windowing, right? There is something which we will cover in second semester, then you will understand it better. For the time being, just take it like this, right? Now, the circuit, right? So there is a single path from source to destination. I told you that. There's a single path from source to destination, sender to destination. This path is known as a virtual circuit, right? Why we say virtual circuit? Because it exists temporarily, right? That is, you see, in TCP, what we do, sender first make destination know, look, I want to communicate with you, right? The destination may say yes or no, right? If you're busy, if it's busy handling other requests, it may decline, right? Otherwise, it may say yes. Then a path is selected, right? Among the many paths, one path is selected from source to destination, and all the packets travel along the path, right? Towards to the destination. It may be a nearby or a remote one, that's not a problem, right? Now, definitely, given that the packets are sequenced, they are sent sequentially one after the other, and they are following a single path, what happens, right? At the destination, on the other side, the destination side, right? The order or sequence is preserved. We don't have to rearrange the packets, they're okay, right? Right, now this circuit, right, this path, when we draw it, is known as a virtual circuit, right? Why we call it virtual? Because TCP, when it has, right, when all the packets has been transmitted to the destination, it has to release the path. You can't take a path and make it permanent for yourself, and you have done your job, right? So you can't keep it, right? You should relinquish it. So it's released so that other communications may use that path again, or segment of that path for future interactions, right? Now, your other one is UDP. In UDP, there is no sequencing, there is no flow control, there's nothing, right? You just send the packets, right? And UDP doesn't, right, rearrange the packet at the other end. It's up to the application on the other side to rearrange it in the proper order if deemed necessary. You see what I mean? But UDP don't have this feature. So it just send the packet, the routers guide the packet towards the destination, right? If sequencing is required, you need to have the other side should be able to do it. I will tell you later more about this. But UDP itself doesn't have that. It's just like a careless guy sending kids to school. Oh, you take this way, other one takes this way. First one may become third one, when they reach the second may become last, or whatever, right? So if sequencing is required on the other side, then, right, the other side need to have certain techniques or mechanisms to rearrange the packet in the proper order, right? So that's it. So UDP, there is no sequencing, right? No acknowledgement of packet. If a packet is lost, it's damn lost. You have to retransmit it manually yourself, right? There's no such thing, right? Now, so the circuit for UDP is known as a datagram subnet, right? Because when we say UDP packets, normally we say datagrams. Datagram is another word for packet, it's not a problem, right? So remember, if you hear the word datagram, it comes from the word telegram, it's a packet itself, right? At times, we also say frame. In fact, frame is more precise than a packet. Later, you will see, right? But we always say packet, that's not a problem. Right, so here we are. Now, What else should I tell you? So in UDP, there's no powerful reservation, no resource reservation like buffer, right? CPU cycles, bandwidth, nothing. Just send the packet, right? So it's the routers that will decide which line is good to send the first packet, which line is good to send the second packet. It will see which line is less congested or has more bandwidth. It depends on what metric it uses, right? It may use a metric like bandwidth. If it uses bandwidth, then the line which has highest bandwidth is the best, right? If it uses metric like reliability, then the line which is more reliability, which is not broken oftentimes, is chosen, right? So if it uses metric like distance, then least distance is used, right? Least distance is best than, right, a long distance, right? So grosso modo, c'est un match fair for passer. Do you have any questions? Right? I don't think so because you have also a lot of questions during the class. So it will reach 80. No, it's not very bad. Right. I hope the others will join. Okay, let's proceed with the lecture now. Regardez, c'est que mon frère là, mon frère Ozzy reference model, ça est un peu, it's a bit it's theoretical, it's easy, right? So we will do it right now. Ozzy reference model, right? The difficult part is the second one, connection-oriented connectionness. Now, I ask you a question. When we send a packet, therefore, what do we need? Do we need IP? Do we need TCP? Do we need UDP or a combination of them? What do you think? Okay, please. Yes, a combination, right? You see, comprends-moi. Écoutez, right, very good answers from all of you, right? Just see. IP, we need it. No way out. So going to some key problem on my knee, right? You see, I had to, when I worked, then I saw this on my own, right? No, I've not seen any textbook which says this, right? They should have said, because this is a confusion. This was a confusion in everybody's mind. What do we use? TCP or UDP only or IP? Where? Right? What? These are questions that arise. You see, IP is always there. IP is a routed protocol. It transports the packet from you to the other side. Now, depending on the application, right? If the application that you're interacting with is, right, or the service that you're using requires TCP, then a TCP header is also included, right? A TCP header is included there, right? The header has many fields. This we will see in second semester, don't worry about it, right? So IP is always there. Why? Because IP provides source address, destination address, time to live, and things among others, right? That along with your data is always there, it's known as a payload, right? But then IP alone is not enough. IP is transporting just like a bus, you know, taking you from Reggio to Port Louis or whatever town you want to go, right? But we need other semantics. If we include TCP, then it will have sequence numbers. It's very good, right? Then we can say which packet has not reached based on the sequence number. Look, I've got packet sequence number 1, 2, 3 I did not get. So it means that the packet has timeout or has lost or has been lost. Something has happened to it. So we retransmit, right? So IP is always there. Then alongside with IP, we can have, right? If you're using TCP, we will have a TCP header. What are the fields in the headers that we will cover later? Right? There are source port, destination ports, and things of the sort. If you're using UDP, that is, for example, when we communicate to a DNS, we use UDP. We don't use TCP. Right? It's just one message, right? One packet. Please, I have this name. Give me the IP address. Right? So it goes to a DNS server, ask, get back whatever it wants, ship it back to the sender. Then it works. So this don't require any resource reservation, resource align, because you are sending one packet to get one packet back. So this is UDP, right? So if you're using UDP, then you will have UDP header. But what always should be there? What? UDP, TCP, or IP? The other, you see, they make things better. But what we need always, type on the panel, IP. IPs should be there, right? You can have all these things, but if you're not transporting them, right, to the destination, routing them towards the destination, the other falls to the ground, right? So IP should be there. Then TCP provides certain functions that IP doesn't offer. UDP doesn't offer much, in fact. You will see the header is only 4 fields, right? When we're doing semester 2. Okay, very good answer from all of you. That's very good. It means that you're understanding things. Right, now let's move on to the lecture. Right now, please, from time to time, Crossref, I'm very happy that the Crossreps, they have created a group, right? I requested them. So I have joined also. So if there are something urgent, I will communicate with you. And I'm very salutary towards you that you're helping me, right? That's good, right? This is the way it should be, right? We should work as a, right? Not as a, we should have a good working relationship, right? I don't want to be a teacher, this teacher. We should have a good, a decent, right? Rational, right? Good one, working relationship. Then things we will prosper. We'll go a long way, right? So thank you, right, for doing this for me. It's good, right? And also, I think we have a faculty representative. So if we have certain recommendations to make pertaining to certain facilities that we want to have, we always have somebody. That's good. Right? Now, let us see the lecture, right? Mon vous faire ça, hein? Get bien, mon vous faire. Était? Aussie reference for that, right? Lecture 1. Après, nous revenons à bout de là. Then we will get back. Sorry, I'm speaking Creole. There is a foreigner in the class I did not know, so she came to me. Okay, so I will speak right in English right, throughout. So let us see. So what we will do is Aussie reference model, which is very simple. Then we will move on to connection or correction oriented. This one, I will just walk over it because I took a lot of time to discuss this, right? Okay, let us see. Are you saying it? Yes? Somebody just turn on your microphone and tell me because I'm not checking the chat panel. Eh?
Yes, we can see.
Yes.
Okay, thank you. Right, très bien. Allez, let's move on. Right. Now, you see, listen to me. During the course of the module, we will cover 3 core reference models, right? The first one is Aussie reference model, Open System Interconnect reference model. This is the most important one, right? It shows how communication takes place, right? When 2 or more entities, or stations, or nodes, or what equipment, right? Intelligent ones, right? Which has IP addresses mostly, are communicating, right? Then we will cover the TCP/IP reference model based on what? Based on the protocols of TCP and IP. And lastly, we will cover the ATM reference model, asynchronous transfer mode reference model, right? Now, the mother of all reference models, right? What do you think amongst these 3 is the mother, the main one, right? Aussie, TCP/IP, or ATM? Type if you're wrong, I will correct you. That's not a problem. Aussie, exactly. Aussie, right. Aussie is a main one, right? So because it's the first one that was built. You see, TCP/IP is a problem with it is that I realized that when I was been working with it. In fact, Aussie is there, came there. It's just like a plan for building a house, right? How much should you dig in the ground, depending on the type of soil that you have, right? What will be the steel bars? What diameter they should be? What is the height of the house, right? What should be the mixture of the concrete? This is it, right? So there is a plan first, right? Directives. Then, based on this, the house is built. Then it will be properly built, right? Because there is something, a guide, right? Made by technically qualified people like engineers or civil engineers or whatever. TCP/IP, what happened? TCP came, IP came, then they realized that there is no reference model. Then the reference model came after the protocol were established, you see? So it's just like you build a house, right? Then you realize, look, there's no manual for it, or a car, right? Then you realize, look, there's no manual. Now we need a manual. Right, so they went ahead and had a reference model for TCP. Now for ATM is not very popular, but it's a good technology to use also. We have a reference model. Now, when we do all these reference model, we will always compare it with TCP with Aussie reference model, which is the mother of reference model. So let's move on to it, right? Right. So I'm sharing the screen. If you don't see, please let me know. Right. Now, okay. So overview of Aussie reference model. So for anyone who wants to be well-versed in computer networks, it is imperative for that person, that individual, to understand the 7 layers of the Aussie reference model. Now, the Aussie reference model, it consists of 7 layers. Each layer has distinct, at times they have slightly overlapping functions also, right? At times they have some overlapping function. That is one function which appears in another one. I don't know. Right? Why is this so? Right. It differs a bit the purpose, but it's like this. So a reference model is a conceptual blueprint of how communication should take place, right? So what should it do? It addresses all the processes required for effective communications and divides these processes into logical groupings called layers, right? Just like if you see a bakery, right? Right. A bakery, it has many units. One unit for mixing up the flour, right? The water and the salt and whatever they have, additives they add there, right? This is one unit, right? You can't have another unit doing the same thing. Right? So another unit is shaping, right? This dough into loaves of bread, right? That is, right? Circular ones, right? Rectangular ones, or whatever you want, right? Then this is passed on a conveyor belt, and it goes to what? An oven, right? Once it's baked, then right, another utility facility removes it from the oven and places it in bags or whatever, right? So there are 5 or 6, you see, different processes, and they are different, right? There are no two things which are doing the same thing, right? But here, as I told you, you will see some small overlap, right? Anyway, this is forgiven because at least it's a good reference model. So vendors design networks products based on the specification of the reference model, right? And it provides a description of how network hardware and software work together in a layered, right, fashion or in a layered way to make communication possible, right? And it also helps with troubleshooting by providing a frame of reference, right, that describes how components are supposed to function, right? So if the components don't function, right, appropriately, then at least we have a frame or a framework or a reference, right, to check what's wrong there. Right. So the Aussie reference model, as I told you before, it has 7 layers. Right? The principles that would apply to arrive at these 7 layers can be briefly summarized as follows. A layer should be created where a different abstraction is needed, right? So we should have a layer, right? Not for the sake of having a layer, but if a different abstraction is needed. That is a different function, maybe if you want to call it another way, right? So each layer should perform a well-defined function, right? Definitely, yes. I just told you about that. I took the example of the bakery, right? The function of each layer should be chosen with an eye towards defining internationally standardized protocol. That is, you see, when you are defining functions, right? Especially in IP networks, right? You can't have a model which doesn't support, right? Protocols like IP, protocols like TCP, protocols like UDP, right? And other protocols also, right? Like OP, like ROP, like ICMP, Internet Control Message Protocol, right? Like DHCP, right? Dynamic Host Communication Protocol. It should support this standardized. Maybe certain protocols which has been designed, right, in a specific country to do a specific task, right? Which is tied to them. It's not international. They may not support. That's not a problem. But internationally recognized, right, and adopted protocols should be supported. Right? So the layer boundary should be chosen to minimize information flow across the interfaces. That's simple. The number of layers should not be large enough that distinct functions need not to be thrown away in the same layer out of necessity, and small enough that the architecture does not become unwieldy, right? So you see, Aussie reference model, if you check it, right, it has 7 layers. The question when I read this for the first time, I was asking myself, why 7? Why not 5? Or why not 1? You see, if we have a centralized layer, then we will have one. Central means everything embodied in one, right? So if you have a centralized layer, then it's not good. Centralization not good because if something crashes, something goes wrong, you don't know what to do, right? It's best to have decentralized. So with decentralized, we have more than one. Now, how they come to these 7 layers, right? Not 8, not 10, or 12, right? It is because you see they have established functions that are needed, right, to support international protocols or standard protocols and so on. Now, they have found that look, one is centralization, everything in one is not good. 2 is we will have common functions in 2 things, right? We will have too many functions in 2. So they have right taken certain functions, put it in one layer, and they came up with 7, which is right, which I think is enough, right? Too much, then we will have repeated some layers won't have any function, so we will repeat the function in another layer, right? So 7 is just fine for it, okay? Now, to reduce the design complexity, most networks are organized as stack of layers also. The purpose of each layer is to offer certain services to the higher layers, shielding those layers from the details of how the offered services are actually implemented, right? Just take the example you see of the bakery, right? Whatever the oven is getting, does it query the other one? Look, did you put the right quantity of salt or water, or do you mix it up? No, it will just take it and do whatever it is supposed to do. It will just bake it, right? Without querying, right, the other units or the other facilities in the bakery, whether they have done something good, right? So what is offered to you, you take it as being right. So this is why you see these layers, they are not interested what the other layers are doing. They're just enforce what they are supposed to do, right? That's all. So layer N on one machine carries a conversation with a layer N on the machine. This you will see soon. So basically, a protocol is an agreement. This is just a definition. Protocol, everybody knows that what is a protocol. It's an agreement between communicating parties of how communication should take place. This I won't ask in the exam. It's just a basic definition. I think everybody knows what is a protocol nowadays, right? So in reality, no data are directly transferred from layer N on one machine to layer N on another machine. In fact, right, each layer passes data and control information to the layer immediately below it until the lowest layer is reached. So in fact, you see when you're sending, it goes from the top layer. Each layer performs certain function. Then it goes to the last layer, which is a physical layer. Then it goes to the network, right? You will see this in the next diagram. Don't worry. Right, you see? So here are the layers, right? So here is, for example, a sending machine, right? And the other one is a receiving machine, right? So what we have, top is application layer. So application protocols will work here, right? Presentation like HTTP, right? Web and so on, right? Presentation layer, session layer, transport layer, network layer, data link layer, physical layer, right? So when we work, everybody, you know this, we work at application level, right? Everything that you open is an application, right? You may call it an application or software, but it's still, right? You may call it an application, there's nothing wrong about that. So you produce certain data, suppose X, Y, Z, hello, how are you, right? So the application layer will do certain things with it, pass it on to the presentation layer, which will add maybe something, right? The session layer will do something else, right? It won't remove what has been added, right, by the application presentation. No, it don't have the right to do that. So when it comes to it, it does its function, right? Normal function, adding a header, adding certain things, right? Certain fields or whatever, right? So then it goes to this is when sending. So when you send, it goes from application to physical. Then it goes to the transport, network, data link, and physical. Now physical, right? Whatever physical layer means, it is this layer which is connected to the network, right? It's called physical. Right, you see? So physical layer, what it does, it takes whatever. Now you actually have a frame, or if you want to call it a packet, but right. So it takes this, right, and converts it to a series of zeros and one, and send it on the line, because the line don't understand what is a packet, what is a frame, right, and so on. So then it goes to the other side, right? Now, when it goes to the other side, it should go to the user on the other side who is working on the application level, right? You always open application to work. So from there, it goes to the physical, to the data link, right? To the network, right? And so on. Now, let me give you an example, right? So suppose what you're sending is A, right? Here. Presentation layer adds something, a header, suppose it adds something B, right? So it becomes AB. This one adds something C, it becomes ABC, right? This one adds something D, ABCD. This one adds something E, ABCDE, right? This one adds something F, ABCDEF. Now, ABCDEF is sent to A, then is converted to a series of zeros and ones. When it reaches here, this one does the converse. So it takes a series of zeros and ones, converts it back to its original form, that is ABCDEF. Then, right, what was the original data here? It was A. So this one, this user who is working on this side here should get A, not all these things that have been added. So this one says, look, here, right, F was added, it strips off F. It knows that here, E was added, so it strips off E. It knows that on the other side has added B here, so it strip off until what remains on top is what was sent, right? So the Aussie reference model is not something physical, right? It's not something physical. Don't do in your machine, right, on your computer in the OS search for Aussie reference model, right? You won't see it. It's not something physical, right? It's just a set of guidelines that application developers use to create and implement applications that run on a network, right? And it also provides, if you want to say, a framework for creating an application and implementing network standard, right, devices and internetworking schemes, right? Now, the Aussie reference model has 7 layers, as I told you before, right? These 7 layers can be normally divided into 2 groups. The top 3 layers, application presentation session, define how applications with end station will communicate with each other, right? They are responsible for applications communicating, right, between hosts, right? So none of these layers know anything about networking and network addresses. They don't add, for example, what is a IP address, right? What is a MAC address, and so on, right? Right? These responsibilities are handled by the 4 bottom layers. That is transport, network, data link, and physical, right? Now, one thing I should tell you also, just listen to me. You see, IP networks, what we have, the internet, in fact, is a big IP network. So, as I told you before, in local area network, like the University of Mauritius, we have a big LAN here, campus network. You can call it a LAN, it's also a big LAN. It's not a problem. In local networks, right, just like we have at the university or in some certain company, we use switches, bridges, repeaters, hubs, and so on. Then we need a router to send the packet to the internet, right? The packet needs to go. If the destination is local, it will go local. If it is outside on Facebook or YouTube or whatever, then it's hard to, right, go outside. So who can make the data go outside? It's not a hub, it's not a bridge, it's not a switch, it's not a transceiver, it's not a repeater, right? It's only a router. Router can find a route for a packet to reach a certain, right, remote destination, which is not on your network here, which is maybe in another country or, right, in another continent, right? So the internet, the main device that the internet has is what? Is routers, right? Routers, right? Because routers only have the capability to route a packet from you here to destination. Otherwise, if you have a network which don't need internet connectivity, right? Right? Suppose you're having some manufacturing secrets and whatever, right? So you don't want people to connect from outside, or otherwise hackers from outside may intrude in your LAN and get whatever manufacturing secrets that you have, right? So if you don't need that, then you don't need a router, right? So the router here, right, for example, at University of Mauritius, it connects to the router of Mauritius Telecom, which in turn connects you to the internet. Routers, right, wherever they are, right, they have to pass through the router of the ISP to go out, right? Hardly you have any routers, which is a node, which is a direct connection to the internet. Normally, you have to channel your data through your router at your establishment, then the router through the ISP, then over to the internet, right? Okay. Now you see, so all devices on IP network should be armed with what is known as an IP address. This is clear to you. There is another address which is at times used. Who can tell me what it is? Another address, right? Not email, right? But another address which is used in computing. Anybody has an idea? Yes, Jayesh Kumar, Albert, yes, very good. Gopal, Mark, yes, right? It's Mark, right? Don't take a question, it's right. Right? Right. Very good. So it's MAC, Media Access Control, right? Right. Now, MAC address, there are many names to it. It's known as, allez, dis-moi one des autres noms pour MAC. Il y en a quelqu'un qui connaît? Pas McDonald's, hein? Allez. What is another name? McDonald's, c'est MC, hein, la MRC. It's known as Media Control Address. Now, what other names do you know for MAC address? It has 4 names. Yes, physical address, right? That's good, Mohammed. Tariq, no? You seem to know quite something in networking. That's very good. Others, please. No. Wireless, Damri, no. Wireless, no. No. Wireless has nothing to do with wired. Eh? We should demarcate this. Right? What we are doing is wired network. I will do wireless also. Don't worry. Second semester. Big part of wireless, you will know it. Right? No, not device ID. Right? I'm sorry. But good try also. Just see. So let me tell you without, otherwise we'll lose too much time. So we have MAC, which is, this keyboard is giving. Then we have another word for it. So first we have MAC, which is Media Access Control Address. Another name for it is hardware address. If you hear hardware address, no, it's not an IP address, right? Right? It's a MAC address itself, right? So another name is Ethernet address, right? And lastly, as many students have correctly pointed out, it's physical address, right? Tout ça là, mêmes affaires, hein? Parce que transfert, puis nous connaissons sur la MAC. Mais le mot qui est plus populaire qui servi, c'est MAC et Ethernet. Right? Physical, c'est bon, on fait tous les cas. Right? Right? Now, you see, MAC address